Hello students, welcome to this lecture in which we're going to talk about line integrals. So let's start with a small example, and in this example we're going to talk about the function f of xy, which is equal to x plus y. So basically this is a slanted plane, and if you want to visualize it using computer you can do that. So you will get something like this. Okay, so this is a slanted plane, and we're going to consider y equals to x squared, which is usually called parabolic cylinder. So basically what we have, if we visualize this, we have can't draw it. So if we have our visualization, so what's going on over here? So this is x, this is y, and this is z. So on the bottom we have a parabola, right? So it looks something like this. So we have a parabola, and so basically if we take and slice, z could be anything, so this parabola is sticking out in the space, right? So we have something like this. So basically if we take a little piece of parabola over here and see how it's sticking out this way, right? So this over here will be our famous f of x sub I star y sub I star as a value on this surface. So we can say that the sliced parabolic cylinder forms a curved wall, curved walls. So the question is, what is the area of this curved wall? What is the area of this curved wall? So where is this curved wall? Where is this area? This area is under the slanted plane, above the x-axis, xy plane, sorry, above the xy plane, and it's between let's set our axis, so between x equal to 0 and x equals to 2. Alright, so we just want to consider this region between 0 and 2. So what would be an approach over here? A nice approach what we can do, we can partition the parabola in xy plane. So we can take a partition of a parabola in xy plane. So it's similar to partitioning the x-axis in calculus 1. Then we're going to approximate the length of each piece of the parabola. So we're going to approximate each piece of the parabola probably the better way to say it would be so let's approximate the length of each piece of the parabola. That's what I wanted to say. So approximate the length of each piece of the parabola with the length of the line segment that connect the endpoints of the piece. So what is it similar to? This is similar to finding the arc length in Calc 2. All right. So what do we get then? So then what we do? We could take a representative z value for each such piece. So we're going to choose x sub I star, y sub I star for each of the pieces. And calculate f at x sub I star, y sub I star to get the z value. Then the last step, finally take the sum like we always do. So take the sum of the areas. Of the rectangular what is the base for this rectangle? The base is length of the segment. And the height is f of x sub I star, y sub I star, like always, right? And if I take the area of each of this piece, we have to take a limit, as the norm of partition goes to 0. Right, so norm partition just means we take more and more pieces. So finally, if the limit exists, it is the area. Alright. So, couple of improvements to this idea. First improvement is let's add a page. So first improvement is it's better to use parametric form. So it turns out to be most convenient to switch everything in parameterized form. Probably we should add vector form, parameterized vector form. So for our example, y equals to x squared, we can think of the vector form v of t equals, so for x we can put t, and for y we have to put t squared, and our t will change from 0 to 2. So now we need the arc lengths of little chunk. So a little chunk of arc length, a little chunk of arc length let's say ds is equal to the magnitude of v prime of t times dt. So in our case, v prime of t is equal to 1 and 2t, right? So what would be the magnitude of v prime of t? The magnitude of v prime of t will be the square root of 1 plus 4t squared. Therefore, our ds is equal to square root of 1 plus 4t squared dt. Now the surface area. So the surface area is equal to the integral along the curve C of xy times the length of this little chunk ds, and we add all of them up, we take a limit, so it's going to be the integral. So in our particular case, it's the integral from 0 to 2 of our function x plus y times the square root of 1 plus 4t squared dt. And these things are called line integrals. So things like that, are called line or path integrals. So what do we mean? We mean that in two space we have an integral over C of f of xy ds, which is equal to the integral over C f of x of t y of t, the length or the magnitude of v prime of t dt. And in three space we have an integral over C of f of x, y, and z ds, which is equal to the integral over C of x of t, y of t, z of t times v prime of t dt. All right. So let's solve an example. Our example would be find the line integral of 2 plus x squared times y ds, where c is the upper half of the unit circle. So basically, picture-wise, we have a unit circle. So this is our C. All right, so we need to parameterize this unit circle with t. So parameterize C. Like always with circles, we think about polar coordinates. So x will be cosine of t, and y will be sine of t, and r is 1. So t is the angle that changes from 0 to pi. So our v function is cosine of t, sine of t. Then from here we know that v prime of t is equal to negative sine of t cosine of t. And then from here we deduct that the magnitude of v prime is equal to square root of sine squared of t plus cosine squared of t, which is square root of 1, which is 1. So now we calculate the line integral over c of 2 plus x squared y ds. So our parameter t changes from 0 to pi. We have 2 plus cosine squared of t sine of t dt. So integral of 2 is easy to take as 2t, but if you think about this function, it's just cosine cubed of t if you think about antiderivative of this function. So you make a change of variables, u equals to cosine squared of t, then du is, just cosine of t. Cosine of t, then du is negative sine of t dt, and so your dt is du over negative sine of t, and your integral of cosine squared becomes u squared times sine of t du over negative sine of t. So sine of t and sine of t goes away, so you get this minus, and antiderivative of u squared is u cubed, so we get cosine cubed of t divided by 3. Cosine cubed of t divided by 3, so u cubed over 3. And this whole expression is evaluated from 0 to pi. Alright, so what do we get? We get pi first, so it's 2 pi, and Cosine of pi is -1/3. Right, so we put a minus, then we plug in 0, so you get 0 for 2t, and we have minus, so you plug in 0 for cosine, and cosine of 0 is 1, so you get 1/3. So what do we get? We get minus and minus is a plus, minus and minus is a plus, so we have 2 plus 2/3. So we used this calculation to get the line integral of this function along the half of the unit circle. Let's look at the next example. In the next example, we have calculate the line integral of x squared z ds, where c connects points 0, 6, and -1, and the point 4, 1, and 5. So if we go back and visualize it, so what do we get? We have x, y, and z, and we move 0 along the x, 6 units along the y, and 1 unit down, so we're somewhere over here, maybe a different color. Then 4, 1, and 5, so we move 4 units along x, 1 unit along y, and 5 units up. So it's somewhere over here, and so we connect these 2 points, where this point is 4, 1, and 5, and this point over here is 0, 6, and -1. All right. So we get these points. So we need the parameters over here, and we need to parameterize this line. So parameterize the line So we can use the vector equation of the line. So vector equation of the line, how can we do that? We can have a starting point, which is 0, 6, and -1 plus t times the vector, where the vector is the difference between this vector and this vector, right? So 4 minus 0 will be 4, 1 minus 6 will be -5, and 5 minus -1 will be 6, so 5 plus 1, right? So basically we can write it as 0 plus 4t if we multiply t and 4, then 6 minus 5t if we take 6 and add -5t, and the last one is -1 plus 6t, where t changes between 0 and 1. T changes between 0 and 1 because if t is 0 we start at this point, and if t is 1 we arrive to this point over here. Alright, so now it's easy to take the derivative of this function. Derivative of this function is 4, -5, and 6 as a vector. then it's easy to calculate the magnitude of this vector, and the magnitude will be square root of 16 plus 25 plus 36, right? So that if it's 50, right, square root of 77, square root of 77. Now we need to take our function f, which is x squared z, and try to write it in terms of the parameter t. So we can take f of x, y, and z, which is x squared z, and for x we put t. I said t, that's not really right. For x we put this value, this is the x, right? So we put 4t quantity squared, and for z we put this value, this is z, so we put -1 plus 6t, and if we multiply it out we're gonna get 16t squared with the minus, and then we have what? We have 16 times 6, it's 16, 36, it's 96 t cubed, 96t cubed. So our line integral becomes f of x, y, and z ds, and we plug everything in, so we get the integral over c it's going to be f of x, y, and z, and for ds we put magnitude of v prime of t dt. It's equal to integral from 0 to 1 of negative 16t squared plus 96t cubed, and this expression times square root of 77 dt. Alright, so we move a little bit forward, so we take square root of 77, we put it outside, then we have negative 16t cubed over 3 plus 96 t to the 4 over 4 from 0 to 1. From 0 to 1, so we have a square root of 77. So let's look. If we plug in 0 over here, everything will zero out, so we don't get anything. So only 1 is important. So we have negative 16 over 3 plus 96 over 4. Right. So we can see that 16 is a common factor, so we can factor out 16. We have square root of 77, so we have negative 1/3 and 96, it's 6 over 4, right? So we divide, we get 3 over 2. 3 over 2. So 16 square root of 77. We have 6 as a common denominator. So this is negative 2 and this is positive 9. Alright. So we have 16 times square root of 77. And we have 7 over 6, so we divide, we get 56 square root of 77 over 3. And that's what we have gotten for this line integral in this example. All right. So suppose we're going to create a different C, right? So for the same example, let's create a different parameterization C2. Parameterization C2. So for C2, let's move in the different direction. Let's move so we're using a different parameterization for C2. So suppose C2 is 0 plus 40 squared, 6 plus 5t squared, and minus 1 plus 60 squared for t between 0 and 1. So basically, if we go back to our picture and grab it from here, okay, so if we take it and grab it and put it back here, so what happened in this what do we get? Basically, what we're trying to achieve, we're going to take a different path, something like this. Alright, so if t is equal to 0, and we get 0, then we get 6, and we get negative 1, so we start over here, and then we trace our curve like this, and when t is equal to 1, we will arrive to 4. Then we need, what was the point? The point was should be minus 5t squared. So if we plug in 1, we're going to get 1, right? 6 minus 5, and here we're going to get 5, right? So we're going to get 5, 4, 1, and 5. Alright, so that's our new parameterization. So I'm just trying to calculate the same integral but over different paths. So what would be my v prime of t? My v prime of t, and this is v of t, So my v prime of t is 8t minus 10t and 12t, and then the magnitude of my v prime is 64t squared plus 100t squared plus 144t squared, and we have to have a square root. So t we can factor out, then 64 and 144 is 208 plus 100, it's square root of 308. So next thing to do is to rewrite our f of x, y, and z which was given by x squared z. So for x squared we put the new x, which is 40 squared, 40 squared squared. That's what we get. And then for z we put minus 1 plus 60 squared. So if we multiply it out, we're going to get negative 16t to the 4 plus 96t to the 6. And we can factor 16 out, so we'll be left with negative t to the 4 plus 6t to the 6. So now we can build our integral over C2, where we have f of x, y, and z ds, which is equal to 16 integral from 0 to 1 of, so 16 is out, so we have negative t to the 4 plus 6t to the 6 dt. Right. We also need, oh, I put dt too early, right? I also need magnitude of v prime, and magnitude of v prime is t times square root of of 308. Right. So t square root of 308. But 308 is divisible by 4. It's 4 times 77, right? 4 times 77. So here we can think of 308 as 4 times 77. All right, so what do we get? Oh, dt. So finally, we set it up. Now it's time to calculate. So we have 16, 308 we'll write as 4 times 77, integral from 0 to 1, and we have negative t to the 5 plus 6t to the 7 dt. So 4 is, square root of 4 is 2, so we have 32 square root of 77. We have negative t to the 6 over 6 plus 6t to the 8 over 8 evaluated from 0 to 1. Alright, so 6 we can divide by 2, 8 we can divide by 2. So finally we have 32 times square root of 77. If we plug in 0, everything will zero out, so we'll keep it. So we have 1 over 6 plus 3 over 4. And we see that 2 is a common factor between 6 and 4, so we can take 1/2 and factor it out. We have 32 square root of 77, and here we have negative 1/3 plus 3/2. Right, so this cancels out, and here we're going to create a common denominator. So we have times 2, so it's negative 2 plus 9 over 6. Negative 2 plus 9 over 6. And you can see we get the same answer as before. 7 over 6, and 6 we can divide. So we have 56 over 3 square root of 77. So what is the takeaway? it take away that it doesn't matter which path to take, right? Which path to take. So line integrals are independent of the path. So you can take any path, you will get the same answer. Alright, probably a good place to stop this long lecture.